Good afternoon. New chapter today. We're talking about functions. This is chapter 7. And here's what I'd like to do. I'd like to define two sets. You can have a set A and let's see, set A is going to be made up of the happy face, and it's going to be made up of the sad face, and then it's going to be made up of the angry face. So we have a set over here with 3 elements in it, and over here, let's have a set B, and why don't we make set B it's made up of an apple, it's made up of a cherry. So we have a set over here with 3 elements in it, and we have a set over here with 2 elements in it. And what I'm going to do is I want to draw a picture. So here is set A. And we have our 3 faces in it. There's angry face, there's sad face, there's happy face. And over here is my set B. And in my set B, I've got my apple and I've got my cherry. I want to play a game here. What I want to do is I want to draw arrows from this set over to this set, okay? And for example, I'm going to draw the happy face over to the apple, and I'm going to draw the sad face over to the apple, and I'm going to draw the angry face over to the cherry. Okay, now what I have here, this is an example of a function. And what a function is a function maps elements from one set to another. Now, the key word here is this word maps. Maps. Another way to say this is it associates. Or we could come over here and we could say it assigns uniquely. Well, what does that mean? Well, what it means is first of all, for every element in this set, I have associated it with an element in this set. But more importantly, what it means is it means that I have assigned this to a single element over here. If we considered an example, let's grab a different color here now. Suppose I told you that the happy face was associated with the apple and with the cherry. Now it would no longer be a function, okay? The idea here is that a function assigns any element from this set over here to just a single element over here. Okay, so in the situation where I have assigned the happy face to 2 elements over here, I no longer have a function. So let's get rid of this line here, if I may. and go back to our original function here. Now, we have some notation that we would use in describing what we have just written down here. First of all, we would say that f, and we'd put a colon here, and we would say a, and then we would draw an arrow here, and we would have b. And what this is saying here is we are saying that f is a function, this particular function that I've drawn here. We assign it a letter name. We can call it f or g. You can call it whatever you like. Sometimes people use Greek letters. You can use Roman letters. In this one, we have a function here that we have called f. And we are saying that f maps the set A, remember this is the set A over here, over to the set B. In fact, if we wanted to, we could be very explicit in specifying this function f, and we use a notation that looks like this. We would say that f of the happy face is equal to the apple. Like that. And over here, we would say that we could specify all three elements of the function here, okay, all three mappings, if you will. We could say that f of, and we say this f of, the sad face, we could say that that's also equal to the apple. And we could come down here and we could say that f of the angry face that's equal to the cherry. Like that. Okay? So we say that f is a function. It uniquely assigns elements from the first set to the second set. We can explicitly give how the function works. We can do it over here like this, using this notation. We could do it over here using this kind of diagram. I believe your book refers to this as an arrow diagram. They are useful. A couple of other things that we would say over here. Remember that a function implies that there's a direction. We're going from someplace to someplace. The place that we're going from is referred to as the domain. So we would say that the domain of f is this set over here called A. Okay? Over here, we sometimes refer to B as the range. Okay? When we get to the next slide, I'll clarify this a little bit more. Your author also talks about the codomain. Codomain. And that's not a term that one hears actually that frequently. You hear the range much more frequently than the codomain. Like that. Okay, function, it maps the domain to the range. It can be represented by this picture here. It can also be explicitly given over here like this. Let's come over here and consider another image. Okay, it was fun having happy faces and cherries and stuff like that, but let's make the sets a little easier for me to draw. So here's a set over here, and we'll call this A. And we'll come over here, and here's an element in A, and here's an element in A, and here's an element in A, and here's B. And here's an element in B. May even could be something like that. So let's say that this goes to that one, And let's say this one goes to that one. And let's say this one goes to that one. Okay, so we have a function here, f, that maps A to B. I'm going to introduce a couple of more definitions over here. These 3 points right here this is sometimes what's referred to as the image of f. Okay, so we could note over here the following. We could say that the image of f is a subset of B. Okay, sometimes it may be all of B, sometimes there may be points in B that aren't in the image of f. Okay, sometimes these points over here, sometimes this is what's referred to as the pre-image. Okay. I think that these definitions are fairly straightforward. Good. Let's consider some examples here. You may remember back in high school, you took an algebra class. Maybe you learned something like this. You learned about equations of lines. Okay, this is an equation of a line. This was the y-intercept. This over here was the slope of the line. Why don't we make this a real example here and say it's like 2x plus 3. Okay, and what I want to do is I'm going to come over here and I'm going to say, I'm going to call this f of x. I'm going to say that this is a function of x. And in fact, what I'm going to say over here is that this is a function that maps real numbers to real numbers. And that shouldn't come as a surprise to you. For example, I could come over here and I could calculate f of 1. And that would be 2 times 1 plus 3. That's equal to 5. I could come over here and I could calculate f of minus 2. And that's going to equal 2 times minus 2 plus 3. Well, that's minus 4 plus 1 is equal to minus 1. I could come over here. Nobody says I have to stick with integers. I could go f of 1/2. That's going to be 2 times 1/2 plus 3. That's equal to 4. I could go f of the square root of 2. And that's equal to 2 times the square root of 2 plus 3. Now you may remember back in high school when you were given something like this, what you would do is you would come over here, you had some graph paper, and this was the x-axis, and what we would do is we would map y is equal to f of x. And what we could actually do is we could come over here and we could talk about ordered pairs. This would be a way to actually draw a picture of this. So in this case, we saw that the number 1 went to the number 5. So that corresponds to the point 1, 5. And we could come over here, and if this is 1 right there, we have 1, 2, 3, 4, 5. That's a point on our line. Likewise, we came over here and we can see that minus 2 got mapped to minus 1. So that means that the point minus 2, minus 1 is also on this. So if I come over here, minus 2, I come down here to minus 1, that point is also on the line. If I come over here, this is telling me that the point 1/2 and 4 is on the line. So if I came over here to 1/2 and went up to 1, 2, 3, 4, it's right over there. And in fact, we know that this thing is a straight line, and I am sure that I am not going to draw a very nice looking thing here, but it would kind of look like that. So that's actually a picture of the function. Now there's something interesting to note here, and this is a good test for telling if something is a function or not when we're talking about functions that are mapping real numbers to real numbers. If it's a function, I'm going to say here functions pass the vertical line test. And what the vertical line test means is the following, that if I go anywhere on that function, if I go anywhere along the x-axis and I draw a vertical line, okay, anywhere, it hits the graph of the function, the picture of the function, which is this straight line. It only hits it in one place. And we can see it hit it once there, and it hit it once there. Let's consider another example here. Suppose again, this is not great artwork, but suppose I were looking at the unit circle, okay? So that right over here is the point 1, 0. Over here is the point 0, 1. Now you may remember if we wanted to describe this thing, we would say that x squared plus y squared is equal to 1. Now, I'm trying to express this as a function, but let's see what happens. Remember, when we were talking about functions that went from the real line to the real line, we ended up doing something like y is equal to f of x. So what I'm going to, and remember, when we wrote y is equal to f of x, what was over here was only an expression involving x. So I come over here and I go, well, I can say that y squared is equal to 1 minus x squared. And then, well, all right, there's a y squared. I want to get it to a y, so I come over here and I take the square root. And I say y is equal to the square root of 1 minus x squared. But what I've written here isn't quite correct. It turns out that when you take the square root, there's a positive root and there's a negative root. Okay? And that's why it's these things over here, this thing over here on the top, and when I say the top, I mean all of this that's y equal to the square root of 1 minus x squared. And the bottom, let's switch colors. The bottom, which starts here and goes all the way over to here, that's y is equal to minus the square root of 1 minus x squared. So the point that we're trying to make here is this is not a function. And that should be clear because it fails the vertical line test. I come over there and I draw, well, that was supposed to be a vertical line. And you can see that it is going to intersect the circle in two places. Okay? Not a function. Now, your book talks about, let's pick a good color, go back to black, that shows up nicely. Okay. Is the function well defined? And what does that mean? It's actually pretty simple. If I come over here, here's A, and I come over here and here is B, and here are 3 points in A, maybe there are 4 points in B, and I say, well, this goes over to here, and I say this goes over to here. Now this is not well defined. And the reason why it's not well defined is we have not said what happens to this point over here. Okay? In such a case, it's not well defined. Here's another case where it's not well defined. Suppose that this went over to here, and it also went over to there. That's also not well defined. Notice that that actually violates our definition for being a function, because what I've done here now is I've actually sent this point to 2 points over here. So not well defined means either some x in the domain is undefined by f or mapped to 2 or more values. Okay? Clear? Good. Let's consider just a couple of more examples of functions. Here's a function f, and this is going to map the natural numbers to the rational numbers. And I'm going to define it as follows. I am going to say f of n is equal to 1/2 to the n. Okay? So notice that everything that goes in here, 1, 2, 3, 4, on and on and on, I map it to this over here, so that f of 1 is equal to 1/2, and f of 2 is equal to 1/2 squared, and f of 3 is equal to 1/2 to the third, which is equal to 1/8. Okay, and you can see that this goes on and on and on. So that's an example of mapping the natural numbers to the rational numbers. How about, let's come up, well, let's use a different letter. Why don't we call it G? How about something that maps the rational numbers to the real numbers? How about G of A over B? Remember, to be a rational number, A and B both have to be integers. Why don't we map that to 3 times A plus the square root of B? Okay, this is certainly a real number. Okay, so that maps from the rationals to the reals. And we could go on and on. There are infinitely many functions to talk about, and we're going to talk about some more.